In 1927, electrons did something no one expected. Not because electrons were particularly rebellious, but because the experiment itself revealed something about the structure of reality that we're still arguing about today. The double-slit experiment is deceptively simple. You fire particles, electrons or photons, toward a barrier with two narrow slits cut into it. Behind that barrier sits a detector screen. If particles behave like tiny bullets, you'd expect two bright bands on the screen, one behind each slit. That's what happens with marbles or grains of sand. But that's not what happens with electrons. Instead, you get an interference pattern. Multiple bright and dark bands spread across the screen, exactly like what you'd see if you dropped two pebbles into a pond and watched the ripples overlap. Where two wave peaks meet, you get reinforcement and a bright band. Where a peak meets a trough, they cancel out and you get darkness. This pattern is the signature of waves, not particles. So you might think, fine, electrons are waves, but here's where it gets strange. You can send electrons through one at a time, waiting seconds or minutes between each launch, so there's never more than one electron in the apparatus. Each electron hits the detector as a single point, a discrete impact like a particle would make. But as you build up thousands of individual impacts, the interference pattern emerges. Each electron somehow produces a result consistent with having traveled through both slits simultaneously, interfering with itself, even though it registers as a single particle when it arrives. The natural next question is, which slit did each electron actually go through? So you set up detectors at the slits themselves to find out. You can use light or other particles to check which path the electron takes. And the moment you do this, the interference pattern vanishes. You're back to two bands, one behind each slit. The electron, once observed, behaves like a particle, taking a single definite path. This is the measurement problem in its most vivid form. Before measurement, the electron seems to exist in what physicists call a superposition, a state described by a wave function that assigns probabilities to finding the electron in various locations. The wave function passes through both slits, interferes with itself, and produces the pattern. But when you measure which slit the electron went through, the wave function appears to collapse into a single, definite outcome. The electron is found at one slit or the other, never both. The word collapse is loaded. It suggests something physical happening, some mechanism that forces the wave function to pick a single reality from the multiple possibilities it was describing. But the Schrödinger equation, which governs how wave functions evolve over time, is smooth and deterministic. It doesn't have collapse built into it. Collapse is something extra, something that seems to happen when a measurement occurs. But the equation itself doesn't tell you what a measurement is, or why it should cause anything special to happen. This is where observation enters the picture, and where things get tangled with misunderstanding. In everyday language, observation implies consciousness, a person looking at something. And because measurement seems to trigger collapse, a seductive idea emerged. Maybe consciousness itself causes the wave function to collapse. Maybe reality doesn't settle into a definite state until a conscious observer sees it. That idea has been wildly popular outside physics and occasionally entertained within it, but it misrepresents what physicists mean by measurement. In quantum mechanics, measurement doesn't require a person or a mind. It requires interaction with a macroscopic system capable of recording information. A detector screen is a measurement device. So is a chunk of metal, or a cloud of gas, or anything large and complex enough to irreversibly register the electron's presence. Consciousness has nothing to do with it. The reason this matters is that the interaction itself creates entanglement. When the electron passes through the slits without being measured, it's an isolated quantum system. Its wave function evolves smoothly, Interference happens, the pattern builds up. But when you put a detector at the slits, the electron interacts with the detector. The detector's state becomes entangled with the electron's state. If the electron goes through the left slit, the detector registers left. If the electron goes through the right slit, the detector registers right. The combined system, electron plus detector, is now in a superposition of two possibilities: electron left and detector shows left, or electron right and detector shows right. But here's the crucial part. The detector is not a single isolated quantum system. It's made of billions upon billions of atoms, all interacting with each other and with the surrounding environment. Photons bounce off it, air molecules collide with it, thermal vibrations jiggle through it. All of these interactions entangle the detector's state with the environment's state. This process, called decoherence, happens incredibly fast, typically within trillionths of a second for macroscopic objects. Decoherence doesn't solve the measurement problem entirely, but it explains why we don't see superpositions in everyday life. Once the detector is entangled with the environment, the interference effects that produce the quantum pattern are effectively erased. The different branches of the superposition, electron left versus electron right, no longer interfere with each other. The system behaves, for all practical purposes, as if the wave function has collapsed into one outcome or the other. The word measurement is misleading because it sounds active, like you're doing something to the system. In reality, measurement is just interaction with something big and messy enough that the quantum coherence gets lost in the noise. The double-slit experiment doesn't show that observation creates reality. It shows that isolating a quantum system is incredibly difficult, and that once you let it interact with the macroscopic world, the delicate quantum effects vanish. Now, none of this tells you what actually happened. Did the electron really go through both slits, or did it secretly go through one slit and we just can't know which? That's not a question the math answers. The wave function is a tool for calculating probabilities. It tells you what you'll measure, not what exists before you measure it. This is the interpretational divide that has persisted for nearly a century. Some physicists, following Bohr, argue that the wave function is the most complete description of reality we can have, and that asking what the electron was doing before measurement is like asking what happens north of the North Pole. The question is malformed. Quantum mechanics describes correlations between measurements, not an underlying reality independent of measurement. Others find this unsatisfying. They want to know what's really there, and so they construct alternative interpretations, frameworks that give different answers to the question of what the wave function represents and what happens during measurement. These interpretations make the same predictions for any experiment you can actually perform, which is why the debate persists. You can't settle it empirically if all the options agree on every measurable outcome. But the double-slit experiment remains the cleanest illustration of the problem. One electron, two slits, an interference pattern that appears when you don't look and disappears when you do. It's not magic. It's not consciousness reaching into the quantum realm. It's physics behaving in a way that doesn't map neatly onto our intuitive categories of particle and wave, definite and indefinite, real and potential. The experiment works exactly the way the math says it should. The trouble is deciding what the math is telling us about the world. The mathematics of quantum mechanics uses something called a state vector to describe a system. For an electron, this state vector exists in an abstract space where different directions represent different possible states the electron could be in. You can think of it like an arrow pointing somewhere in this space, though the space has far more dimensions than the three we move through. When you measure a property like position or spin, you don't just get any value. You get one of a specific set of allowed values, called eigenvalues. Before measurement, the state vector might be pointing in a direction that doesn't align with any single eigenvalue. Instead, it's a combination, a superposition, of multiple possible outcomes. The math lets you calculate the probability of getting each outcome, but it doesn't tell you which one will occur on any single trial. Superposition is often described in mystical terms. The electron is in multiple places at once. The particle exists in all possible states simultaneously. Reality is fundamentally blurred until observation forces it to sharpen. But these descriptions smuggle in metaphysical assumptions that aren't actually in the equations. The wave function is a mathematical object that assigns complex numbers to different possible measurement outcomes. Whether those possibilities correspond to something physically real existing in multiple states, or whether the wave function is just a calculational tool that predicts what we'll observe, is not something the math itself decides. Take the example of an electron's spin. Spin is an intrinsic property of particles, something like angular momentum, but not quite, since electrons aren't literally spinning balls. If you measure spin along a vertical axis, you get one of two results: spin up or spin down. Before measurement, the electron can be in a superposition of up and down. The state vector points in a direction that's some combination of these two possibilities. Here's where it gets interesting. You can also measure spin along a horizontal axis, left or right. And if you prepare an electron in a definite spin-up state along the vertical axis, then measure it horizontally, you get a 50-50 chance of finding it spin left or spin right. The electron that was definitely up along one axis is in a superposition along a different axis. The choice of what to measure affects what states count as definite and what counts as superposition. This isn't because measurement disturbs the electron in some clumsy mechanical way. It's because the electron doesn't have definite values for spin along multiple axes simultaneously. The math doesn't allow it. If spin up along the vertical axis is one state, and spin left along the horizontal axis is a different state, then knowing one tells you nothing certain about the other. The superposition isn't ignorance about which state the electron is secretly in. It's a statement that the electron's state genuinely doesn't align with either outcome for the measurement you're about to make. Now, entanglement takes this further. Entanglement occurs when two particles interact in such a way that their states become correlated, and those correlations can't be described by treating each particle as having its own independent state. The combined system has a definite state, but neither particle individually does. The classic example involves two electrons prepared so their total spin is zero. If you measure the first electron and find it spin up along some axis, you instantly know the second electron will be spin down along that same axis. This happens even if the electrons are separated by kilometers or light years. Measure one, and you immediately gain information about the other. This is often framed as spooky action at a distance, as if measuring one electron sends some signal faster than light to affect the other. But that's not what's happening. The correlation was established when the particles interacted and became entangled. After they separate, no signal passes between them. The measurement on the first electron doesn't change the second electron's state. It reveals information about the combined state that was there all along. Here's the key point. Before you measure, you can't say that the first electron is secretly spin up and the second is secretly spin down, and you just don't know which is which. If that were true, the particles would behave like classical objects with hidden properties. But experiments, particularly tests of Bell's inequalities, show that the correlations between entangled particles are stronger than any classical hidden variable theory can produce. Particles don't have definite individual spins before measurement. The entangled state is a genuine two-particle superposition, and the measurement outcomes are correlated in a way that can't be explained by pre-existing hidden properties. Entanglement doesn't allow faster-than-light communication. You can't use it to send information. When you measure the first electron, you get a random result, spin up or spin down, with 50-50 odds. The person measuring the second electron also gets a random result. Only when you compare notes, through ordinary, slower-than-light communication, do you see the perfect correlation. From any single location, entanglement looks like random noise. The correlation is only visible when you bring the two sets of measurement results together. The strangeness of entanglement isn't that particles magically affect each other across space. It's that quantum mechanics describes correlations that can't be reduced to properties of individual particles. The whole is not just the sum of its parts. The combined state contains information that isn't stored locally in either particle. This non-locality is built into the structure of the theory, and Bell's theorem tells us that any theory that reproduces quantum predictions must have this non-local character, at least in some sense. Superposition and entanglement are often invoked to justify wild claims. Quantum healing, consciousness collapsing wave functions across the universe, objects existing in multiple places because of superposition. But these ideas misapply the math. Superposition describes a state relative to a measurement you haven't made yet. It's not a claim that reality is literally splitting or blurring. And entanglement describes correlations, not causal influences or mystical connections. The math works. It makes predictions that have been confirmed to absurd precision across decades of experiments. But the math is written in a language that doesn't translate neatly into everyday intuitions about objects and properties. A superposition isn't multiple realities layered on top of each other. It's a single mathematical state that doesn't correspond to any single classical outcome. Entanglement isn't a bond or connection between particles. It's a feature of the state space itself. The fact that composite systems can have properties that aren't reducible to the properties of their components. You can think of the wave function as a map of possibilities, weighted by probabilities. Or you can think of it as a complete description of something physically real but unobservable. Or you can think of it as a tool for organizing your knowledge about what measurements will yield. The math doesn't force you to choose. What it does force you to accept is that quantum systems don't behave like classical objects, and the properties we measure aren't necessarily sitting there waiting to be revealed before we measure them. Superposition and entanglement aren't mysteries in the sense that we don't understand how they work. We understand the math perfectly. The mystery, if there is one, is ontological. What does it mean for something to be in a superposition? What kind of thing is an entangled state? These aren't questions about physics. They're questions about what physics is describing, and on that front, the theory itself stays quiet. In the mid-1920s, quantum mechanics emerged from the work of Heisenberg, Schrödinger, Dirac, and others. But it was Niels Bohr who shaped how most physicists learned to think about what the theory meant. His interpretation, developed largely in dialogue and debate with Heisenberg, became known as the Copenhagen interpretation, though it was never a single, unified doctrine. It was more a constellation of ideas about measurement, complementarity, and the limits of what we can know or meaningfully ask. Bohr's central claim was that quantum mechanics is complete. The wave function provides the fullest possible description of a quantum system. There's no hidden layer of reality beneath it, no deeper variables waiting to be discovered that would tell you what the electron was really doing before you measured it. The theory doesn't describe an objective reality independent of observation. It describes the results of measurements, the correlations between preparation and detection, and nothing more. This was a radical move. Classical physics assumed that objects have definite properties whether or not anyone measures them. A planet has a position and a velocity. A ball has a temperature and a mass. These properties exist independently, and measurement simply reveals them. Bohr argued that this assumption breaks down at the quantum level. You can't meaningfully ask where the electron is before you measure its position, because position isn't a property the electron possesses in the absence of a measurement context. He introduced the idea of complementarity to explain why. Certain properties, like position and momentum, or wave-like and particle-like behavior, are complementary. You can set up an experiment to measure one or the other, but not both simultaneously with arbitrary precision. The choice of measurement apparatus determines which aspect of the system reveals itself. The electron isn't secretly both a particle and a wave. It exhibits particle behavior in some experimental contexts and wave behavior in others, and these behaviors are mutually exclusive but equally necessary for a complete empirical description. This wasn't just a practical limitation on measurement precision. Bohr insisted it was a fundamental feature of reality. The properties we observe aren't intrinsic to the quantum system alone. They emerge from the interaction between the system and the macroscopic measuring apparatus. The apparatus is described classically with definite pointer positions and dial readings, because that's the only way we can communicate about observations. But the quantum system doesn't have definite values for these properties until the interaction occurs. Heisenberg contributed the uncertainty principle, which quantified this complementarity. You can't know both position and momentum to arbitrary precision. The more accurately you pin down one, the more uncertain the other becomes. This isn't because your measurement disturbs the system, though that's a common misunderstanding. It's because position and momentum are represented by non-commuting operators in the mathematical structure of quantum mechanics. The theory itself forbids certain combinations of knowledge. The uncertainty isn't in our measurements, it's in the nature of what can be simultaneously real. Bohr also argued against realism, at least in its classical form. Realism is the idea that the world has definite properties independent of observation, and that science discovers those properties. Bohr didn't say the world doesn't exist when you're not looking. He said that attributing definite, unobserved properties to quantum systems leads to contradictions, and that quantum mechanics only makes predictions about what happens when systems interact with measuring devices. The wave function isn't a picture of reality. It's a tool for calculating the probabilities of measurement outcomes. This was philosophically disturbing to many physicists, including Einstein, who famously objected that God doesn't play dice. Einstein believed in an objective reality, a universe with definite properties existing independently of whether anyone observes them. He thought quantum mechanics was incomplete, that there must be hidden variables specifying the outcomes in advance, and that our ignorance of these variables forces us to use probabilities. Bohr disagreed. He argued that the probabilities in quantum mechanics aren't due to ignorance. They're irreducible, baked into the structure of the theory. The debates between Bohr and Einstein stretched over decades and became legendary. Einstein proposed thought experiments designed to show contradictions or incompleteness in quantum mechanics. Bohr responded by carefully analyzing each scenario and showing that the theory remained consistent. One famous exchange involved Einstein suggesting a box with a shutter that opens briefly to let a photon escape, challenging whether energy and time could both be precisely known. Bohr countered by invoking general relativity, showing that the gravitational effect of the box's mass on time measurement introduced exactly the uncertainty required by Heisenberg's principle. But here's where things get historically tangled. The Copenhagen interpretation, as taught in textbooks, often goes beyond what Bohr actually said. Bohr was cautious and philosophical, emphasizing the role of classical concepts in framing quantum phenomena. He didn't claim that consciousness causes wave function collapse. He didn't say that measurement requires a human observer. Those ideas crept in later, partly through the work of physicists like John von Neumann and Eugene Wigner, who speculated about consciousness playing a role in resolving the measurement problem. Von Neumann's influential textbook on quantum mechanics included a proof that hidden variables were impossible, which seemed to cement Copenhagen as the only viable interpretation. Wigner went further, suggesting that consciousness might be necessary to collapse the wave function, since otherwise you'd have an infinite regress of quantum systems measuring other quantum systems with no definite outcome ever emerging. These ideas were speculative, never mainstream among working physicists, but they entered popular culture and became conflated with the Copenhagen interpretation itself. Bohr never endorsed consciousness-based collapse. He treated measurement as a physical process involving macroscopic apparatus, not minds. The apparatus is described classically because it's large and complex enough that quantum coherence is destroyed by environmental interactions. This is essentially decoherence, though Bohr didn't have that term or the detailed mathematical framework that came later. His point was that the boundary between quantum and classical isn't arbitrary or consciousness-dependent. It's set by the scale and irreversibility of the interaction. The Copenhagen interpretation dominated physics for decades because it worked. It told physicists how to calculate, how to set up experiments, how to interpret results. It avoided metaphysical commitments about unobservable reality and focused on what could be empirically tested. Shut up and calculate, as the saying goes, though Bohr himself would have objected to that phrasing. He cared deeply about interpretation, but he insisted on staying grounded in what experiments could actually distinguish. The trouble is that the interpretation left fundamental questions unanswered. What exactly counts as a measurement? Where does the quantum classical boundary lie? Why does the wave function appear to collapse when it's governed by an equation that doesn't include collapse? Bohr's response was essentially that these questions mistake the nature of quantum mechanics. The theory describes phenomena, not reality. Asking what happens before measurement is like asking what color is the number 7. It's a category error. Not everyone found this satisfying. Some physicists wanted a clearer ontological picture, a story about what's actually happening, not just what we'll observe. And so alternative interpretations began to emerge, each trying to preserve the empirical success of quantum mechanics while offering a different account of what the theory describes. But Copenhagen remained the default, the interpretation built into textbooks and taught to generations of physicists, often without making clear that it was an interpretation at all, rather than just what quantum mechanics says. The legacy is mixed. Copenhagen freed physics from the need to visualize quantum processes in classical terms, allowing the mathematical formalism to guide the science without metaphysical baggage. But it also fostered a kind of anti-realism that made quantum mechanics seem more mysterious than it needed to be. And it inadvertently opened the door to mystical misinterpretations by leaving the role of observation ambiguous. Bohr tried to walk a careful line. Popular culture and some physicists crossed it. In 1957, a graduate student named Hugh Everett submitted a doctoral thesis that proposed something outrageous. He suggested that the wave function never collapses. Every possible outcome of every quantum measurement actually occurs. When you measure an electron's spin and find it pointing up, there's another version of you, in another branch of reality, who measured it pointing down. The universe splits, constantly and endlessly, into parallel worlds corresponding to every quantum possibility. This is the many worlds interpretation, and it's either the most elegant solution to the measurement problem or the most extravagant ontological commitment ever made in physics, depending on who you ask. Everett started from a simple observation. The Schrödinger equation is deterministic and linear. It evolves the wave function smoothly over time without any collapses or jumps. But the Copenhagen interpretation says that when a measurement happens, the wave function suddenly collapses into one outcome. This collapse isn't part of the Schrödinger equation. It's an additional postulate grafted onto the theory to match what we observe. Everett asked, what if we just take the Schrödinger equation seriously and let it apply to everything, including the measuring apparatus and the observer? Here's how it works. Before you measure the electron's spin, it's in a superposition of up and down. When you measure it, you and your measuring device become entangled with the electron. The combined system enters a superposition. One branch where the electron is up and you see up, and another branch where the electron is down and you see down. Both branches exist. Both are equally real. But they no longer interact with each other because they've decohered. Each version of you experiences only one outcome and sees what looks like a collapse. But from outside the system, nothing collapsed. The wave function of the entire universe just kept evolving smoothly. This eliminates the measurement problem in a technical sense. There's no mysterious collapse, no special role for measurement, no boundary between quantum and classical. Everything is quantum. The universe is one giant wave function, evolving according to the Schrödinger equation. What we call measurement is just entanglement between subsystems, and what we call outcomes are branches of the universal wave function that have decohered and can no longer interfere. The cost is that you have to accept an enormous proliferation of worlds. Every quantum event with multiple possible outcomes spawns new branches. An electron decays or doesn't decay, and both happen in different branches. A photon hits a detector or misses it, and both occur in different branches. Multiply this by every quantum interaction everywhere in the universe, and you get an incomprehensibly vast multiverse, constantly branching into more and more versions of reality. Everett called these branches relative states rather than parallel worlds. The idea was that there's one universal wave function, but different branches of it correspond to different classical realities. The electron's state is relative to your state. From your perspective, the electron has a definite spin after measurement. From the perspective of the universal wave function, both outcomes exist in superposition, correlated with different versions of you. The interpretation solves several conceptual problems. It's fully deterministic. There's no randomness in the theory itself, only the appearance of randomness from the perspective of observers within a single branch. It treats observers as physical systems, subject to the same quantum laws as everything else, with no special status for consciousness or measurement. And it's ontologically parsimonious in one sense. There's just the wave function, evolving according to one equation, with no additional collapse postulate. But it raises new problems. The most obvious is, why do we experience probabilities? If both outcomes happen, why does it feel like the electron had a 50% chance of being spin up? Everett and later proponents have offered various answers, mostly based on the idea that the measure or weight of a branch in the wave function determines how likely you are to find yourself in that branch. But this is subtle. You can't say you had a 50% probability of ending up in the spin-up branch because both versions of you exist. The probabilistic language has to be reinterpreted, perhaps as a statement about rational betting behavior or self-location uncertainty within the multiverse. Another problem is the sheer ontological cost. Copenhagen says the wave function isn't a complete description of reality, but avoids committing to what is. Many Worlds says the wave function is reality, and reality is incomprehensibly vast. Every possible history of the universe exists somewhere in the multiverse. You exist in countless versions, experiencing every possible sequence of quantum outcomes compatible with the laws of physics. This is, to put it mildly, extravagant. Some physicists find this extravagance beautiful. The theory is maximally simple in its postulates. One equation, one wave function, no collapse. The complexity is in the consequences, not the assumptions. It's like how general relativity has beautifully simple field equations, but those equations imply black holes, gravitational waves, and the expansion of the universe. Many Worlds has one law, the Schrödinger equation, but that law implies a multiverse. Others find it absurd. The branches are causally disconnected. You can never visit another branch or communicate with another version of yourself. The splitting is unobservable in principle. The theory postulates an infinity of undetectable worlds to avoid adding a single collapse postulate to the formalism. It's solving a problem by multiplying entities far beyond necessity, a violation of Occam's razor on a cosmic scale. There's also the question of what exactly branches and when. Everett's original work was vague on this. Later proponents, particularly David Deutsch and David Wallace, have tried to make it more precise using decoherence theory. Idea is that branching occurs when systems become sufficiently entangled with their environment that different branches can no longer interfere. This happens continuously and doesn't require anything special about measurement. Every interaction that leads to decoherence creates branching. But decoherence doesn't tell you when branching is complete or how to count branches. The wave function is a continuous object, and branches emerge gradually as coherence is lost. There's no sharp moment when one world becomes two. This makes it hard to say exactly what the ontology of many worlds is. Are there literally separate worlds, or just one world with a very complicated wave function? Different proponents give different answers. Despite these issues, many worlds has gained significant traction, especially among physicists working on quantum information and quantum computing. It's the interpretation that takes the formalism most seriously, treating the wave function as physically real rather than a calculational tool, and it avoids the main conceptual difficulties of Copenhagen: the measurement problem, the quantum classical boundary, and the special status of observers. It also makes strange predictions about probability and decision-making. If every choice you make spawns branches where you made different choices, and all branches are equally real, then in what sense did you make a choice? There's a version of you that chose otherwise. Some proponents bite the bullet and say that personal identity becomes branching and plural. You're not a single person with one future, but a branching tree of people, all equally you, experiencing different outcomes. This connects to bizarre thought experiments. Quantum suicide, for instance, where you set up a device that kills you if a quantum measurement goes one way, but not the other. From your subjective perspective, you can only experience the branch where you survive. Run the experiment 1,000 times, and in one branch, you survive all 1,000 trials, no matter how unlikely. Of course, there are 999 other branches where you're dead, but you don't experience those. Most physicists consider this thought experiment perverse and not a reason to take many worlds seriously. But it illustrates the strange implications. The interpretation remains controversial. Surveys of physicists show it's gained ground, with maybe a quarter to a third favoring it, but it's far from consensus. Some physicists love the mathematical elegance and the way it eliminates special roles for measurement. Others think the proliferation of worlds is too high a price, especially when there's no empirical difference between many worlds and other interpretations. And some simply don't care, treating interpretations as metaphysical speculation irrelevant to actual physics. Everett himself had a complicated relationship with his idea. He left academic physics after his thesis, partly because the interpretation was ignored or dismissed by most of the physics community for decades. It wasn't until the 1970s and 80s, after his death, that it began to be taken seriously. Now it's one of the major contenders, defended by prominent physicists and philosophers, taught in graduate courses, and debated in countless papers. Whether it's true is another question entirely, and one that may not even be decidable. In 1927, the same year quantum mechanics was being formalized, a French physicist named Louis de Broglie proposed something different. He suggested that particles are always particles, with definite positions at every moment, but they're guided through space by a real physical wave. The wave evolves according to the Schrödinger equation, and the particle follows trajectories determined by the wave's structure. Both wave and particle exist simultaneously, not as complementary aspects, but as distinct elements of reality. This was pilot wave theory, also called de Broglie-Bohm mechanics, or Bohmian mechanics, after David Bohm revived and extended it in the 1950s. It's a fully deterministic interpretation where nothing is fundamentally random. The appearance of randomness in quantum measurements comes from our ignorance of the particle's initial positions, not from any intrinsic indeterminacy in nature. The theory works like this. Every particle has a definite position at all times, even when it's not being measured. There's no superposition of positions, no collapsing wave function. The particle is always somewhere specific. But its motion isn't determined by forces in the classical sense. Instead, it's guided by a quantum potential derived from the wave function. The wave spreads out through space, passes through both slits in the double-slit experiment, and interferes with itself. The particle follows one specific path through one specific slit, but which path it follows depends on the structure of the interfering wave on the other side. This explains the interference pattern without invoking superposition of the particle itself. Thousands of particles, each starting from slightly different initial positions, follow different trajectories, guided by the same pilot wave. The trajectories cluster in regions where the wave function has high amplitude, and avoid regions where it's zero. Build up enough particles, and you see the interference bands, even though each individual particle took a definite path. When you measure which slit the particle goes through, you introduce a new element into the system. The measuring device interacts with the pilot wave, changing its structure. The interference pattern disappears, not because observation collapses anything, but because the measurement physically alters the wave that guides the particles. The wave no longer has the interference structure, so the particle trajectories no longer cluster into bands. The mathematics of pilot wave theory reproduces all the predictions of standard quantum mechanics exactly. It's empirically equivalent, at least for non-relativistic quantum mechanics. This means you can't do an experiment to tell whether Copenhagen or pilot wave theory is correct. They make identical predictions for every measurement you could perform. The difference is purely in the ontology, in what the theory says exists. Pilot wave theory is explicitly realist. Particles have definite positions. The wave function represents a real physical field. There's an objective reality independent of measurement. And it's deterministic. If you knew the initial position of every particle and the initial form of the wave function, you could, in principle, calculate all future positions. The probabilities in quantum mechanics arise because we don't know initial positions. We only know the probability distribution given by the wave function, squared. This sounds appealing if you're uncomfortable with Copenhagen's instrumentalism or many worlds extravagance. You get a clear picture of what's happening. Particles move along trajectories, waves guide them. Measurement reveals pre-existing positions. No collapse, no branching universes, no special role for observers. But there are costs. The theory requires hidden variables, the exact positions of particles, which quantum mechanics says we can't know. It's non-local in a very explicit way. The pilot wave for a many-particle system exists in configuration space, a space with 3 dimensions for each particle. For 2 entangled particles, the wave lives in a 6-dimensional space. The motion of one particle depends instantaneously on the positions of all other particles it's entangled with, no matter how far apart they are. This non-locality was initially thought to be a fatal flaw. Einstein, Podolsky, and Rosen argued in 1935 that if quantum mechanics were complete, it would require non-local influences, which they thought was absurd. They intended this as a reductio ad absurdum, proof that quantum mechanics must be incomplete. But John Bell proved in 1964 that any hidden variable theory reproducing quantum predictions must be non-local. Experiments testing Bell's inequalities have confirmed this. The correlations between entangled particles are stronger than any local hidden variable theory can produce. Pilot wave theory embraces non-locality openly. When you measure one particle of an entangled pair, the wave function for the entire system changes instantaneously everywhere. This affects the quantum potential guiding the other particle, even if it's light years away. But you still can't use this for faster-than-light communication, because you don't control which outcome you get. The measurement reveals information about pre-existing correlations, not new information created at a distance. Another issue is that the particle trajectories are unobservable. You can calculate what paths particles would take in pilot wave theory, and they're often bizarre. In the double-slit experiment, particles going through one slit can be deflected by the wave that went through the other slit, following curved paths that look nothing like classical trajectories. But you can't measure these paths directly without disturbing the system, and if you disturb the system, you change the pilot wave and the trajectories themselves. This makes the hidden variables truly hidden. You can't verify that particles actually have definite positions by measuring them continuously, because continuous measurement changes the dynamics. The theory predicts the same measurement outcomes as standard quantum mechanics, which treats position as not having a definite value until measured. The trajectories are part of the ontology, but they're invisible. There's also the problem of extending the theory to relativistic quantum mechanics and quantum field theory. De Broglie and Bohm developed pilot wave theory for non-relativistic particles. Making it relativistic is difficult because special relativity treats space and time on equal footing. But pilot wave theory requires a preferred notion of simultaneity to define instantaneous non-local influences. Various proposals exist, but none are as clean or well-developed as the non-relativistic version. Despite these difficulties, pilot wave theory has maintained a small but dedicated following. It's defended by physicists and philosophers who want a realist interpretation without many worlds' ontological excess. It shows that deterministic hidden variable theories are possible, contrary to widespread claims based on misinterpretations of von Neumann's proof. And it provides a concrete example of how quantum mechanics could be describing an underlying reality, not just measurement outcomes. The theory also makes clear what non-locality means in quantum mechanics. It's not that influences propagate faster than light. It's that the state of the universe at one location depends on the configuration of distant parts in a way that can't be factored into local properties. The wave function is fundamentally global, encoding correlations that can't be reduced to information stored in separate regions of space. Some researchers have explored whether pilot wave theory might make different predictions in extreme regimes, like quantum cosmology or quantum gravity, where the interpretation might matter. So far, no clear testable differences have emerged. Others have investigated whether the theory could explain apparent anomalies in experiments, like unexpected patterns in particle arrival times. Again, nothing definitive. The interpretation remains a minority view, but it's philosophically significant. It proves that quantum mechanics doesn't force you into instrumentalism or many worlds. You can have a theory that's realist, deterministic, and empirically adequate, though you pay for it with non-locality and hidden variables. Whether those costs are worth it depends on your philosophical priorities, and that's not a question physics itself can answer. Bohm himself thought the theory was incomplete, a stepping stone toward a deeper theory where the quantum potential emerges from some underlying process. He spent much of his later career speculating about implicate and explicate orders, holistic, undivided wholeness, and other ideas that never gained traction in mainstream physics. But the pilot wave theory itself, stripped of Bohm's later metaphysics, remains a viable interpretation, a proof that the quantum world could be deterministic and realist, even if we'll never see the hidden trajectories that determinism implies. Quantum systems are fragile. A single electron in a superposition of two spin states, isolated from the rest of the universe, maintains that superposition indefinitely. But isolate is the key word. The moment that electron interacts with its environment, even slightly, the superposition begins to decay. Interference effects fade. The system starts behaving classically, as if it had collapsed into one definite state or another. This process is called decoherence, and it happens fast, extraordinarily fast. For a dust particle floating in air at room temperature, decoherence destroys quantum coherence in about 10 to the minus 31 seconds. That's a trillionth of a trillionth of a trillionth of a second. For a molecule of Buckminster fullerene, a soccer ball-shaped arrangement of 60 carbon atoms, experiments have measured decoherence times of around a millisecond under carefully controlled conditions. Let it interact with air molecules or stray photons, and coherence vanishes almost instantly. This explains why you don't see superpositions in everyday life. Not because observation magically collapses wave functions, and not because large objects somehow fail to obey quantum mechanics. They obey it perfectly. The problem is that macroscopic objects are constantly interacting with their surroundings. Air molecules collide with them. Photons scatter off them. Thermal vibrations jiggle through them. Each interaction entangles the object's quantum state with the environment state, and once you have enough entanglement, the different branches of the superposition no longer interfere. The system decoheres. The mathematics of decoherence is straightforward. Start with a quantum system in a superposition, say an atom in a combination of two energy states. The system's density matrix, a mathematical object encoding all statistical information about the state, has off-diagonal terms representing quantum coherence. These terms are what allow interference. When the system interacts with the environment's degrees of freedom become correlated with the system's state. If the atom is in energy state 1, the environment ends up in some corresponding state. If the atom is in energy state 2, the environment ends up in a different state. Now here's the crucial part. The environment is huge, with an enormous number of degrees of freedom. You can't keep track of all of them. When you average over the unknown environmental states, a process called tracing out the environment, the off-diagonal terms in the density matrix shrink toward zero. Coherence is lost. The system looks like a classical mixture, as if it had a definite energy, but you just don't know which one. This happens even though the combined system, atom plus environment, still has a perfectly well-defined quantum state evolving unitarily according to the Schrödinger equation. No collapse has occurred at the fundamental level. But from the perspective of the atom alone, ignoring the environmental degrees of freedom you can't measure, the superposition is gone. The system behaves classically for all practical purposes. Decoherence is environment-induced, but it doesn't require anything special about the environment. Any system with many degrees of freedom that couples to the quantum system will cause decoherence. Air works. Photons work. A surrounding electromagnetic field works. Even the vacuum fluctuations of quantum fields can do it, though usually more slowly. The key is that information about the quantum system leaks into the environment and becomes inaccessible, destroying the correlations needed for interference. The theory was developed starting in the 1970s by physicists like Heinz-Dieter Zeh, Wojciech Zurek, and others, though hints of it appeared earlier. It explains why macroscopic superpositions are so hard to create and maintain. It's not a fundamental limit, it's a practical one. If you can isolate a system perfectly, keeping it from interacting with anything, quantum coherence persists. This is why quantum computing is difficult. Qubits need to stay in superpositions long enough to perform computations, but any interaction with the environment causes errors through decoherence. Decoherence also explains pointer states, the special quantum states that survive interaction with the environment. Not all superpositions decohere at the same rate. Some states are robust, decohering slowly or not at all. These are typically the states corresponding to classical properties like position or energy. A superposition of two different positions decoheres very rapidly, while a superposition of two momentum states might decohere more slowly. This is why position looks classical and definite, while momentum can exhibit quantum uncertainty more readily in certain experiments. The pointer states are selected by the interaction Hamiltonian, the mathematical description of how the system couples to the environment. For a dust particle, position is a pointer state because photons scatter differently depending on where the particle is. The position becomes correlated with the environment almost immediately. For an electron in an atom, energy eigenstates are often pointer states because they couple weakly to the electromagnetic field. The system can remain in a definite energy state for a long time without decohering. This gives a natural explanation for why certain quantities, like position, seem classical while others remain quantum. It's not arbitrary. It's determined by the physics of the interaction. The environment effectively performs a continuous measurement, constantly monitoring certain properties and destroying coherence in others. This is sometimes called environment-induced superselection. But here's what decoherence doesn't do. It doesn't solve the measurement problem completely. It explains why we don't see superpositions of macroscopic pointer readings. After a measurement, the combined system of particle plus apparatus decoheres rapidly, and each branch of the superposition, corresponding to a different measurement outcome, becomes effectively isolated. But decoherence doesn't tell you why we experience one outcome rather than another. In many worlds' language, decoherence explains why the branches separate and stop interfering, but all branches still exist. Each contains a version of you who saw a definite outcome. Decoherence doesn't pick one branch as real. In Copenhagen language, decoherence explains why the wave function looks like it collapsed, but it doesn't explain the collapse itself. The system is still in a superposition at the fundamental level, just one where the different terms are entangled with distinct environmental states. In pilot wave theory, decoherence explains why you can't see the interference between trajectories that went through different slits, but the particles always had definite positions anyway. Decoherence is interpretation neutral in that sense. It's a physical process that all interpretations agree on. Where they differ is in what that process means for the nature of reality. The timescale of decoherence depends on the system's size, the strength of its coupling to the environment, and the environment's temperature. Larger objects decohere faster because they have more surface area interacting with surrounding particles and fields. Hotter environments cause faster decoherence because thermal photons and vibrations are more energetic and numerous. This is why quantum effects are easier to observe at low temperatures and in small systems. Not because quantum mechanics stops applying, but because decoherence is slower. Experiments have confirmed decoherence predictions in remarkable detail. One famous example involves sending molecules through a double-slit apparatus. When the molecules are cold and isolated, you get an interference pattern. Heat them up or let gas molecules scatter off them, and the pattern disappears. The rate at which coherence is lost matches theoretical predictions based on decoherence rates. Another example is cavity quantum electrodynamics experiments, where atoms interact with photons in a mirrored cavity. By controlling the interaction strength and the number of photons, researchers can watch decoherence happen in real time. They see the off-diagonal terms in the density matrix decay exponentially, exactly as the theory predicts. Decoherence also explains why quantum mechanics looks classical at large scales without requiring a sharp boundary. There's no magic size or mass where quantum becomes classical. It's a smooth transition determined by how fast the system decoheres compared to how fast quantum effects would show up. For a dust particle, decoherence is so fast that you'd never see quantum behavior. For an electron, you can isolate it well enough that quantum effects dominate. This has practical implications. Quantum technologies require fighting decoherence, using error correction codes and careful isolation to preserve coherence long enough to do useful work. Understanding decoherence is essential for building quantum computers, quantum communication systems, and ultra-precise quantum sensors. The theory isn't just philosophical, it's engineering. But philosophically, decoherence shifts the measurement problem rather than solving it. The question is no longer why superpositions disappear. We understand that through environmental interaction. The question is what it means for superpositions to disappear from our perspective while still existing in the universal wave function. Decoherence makes the quantum to classical transition comprehensible physically, but it doesn't resolve the interpretive puzzles about what quantum mechanics is describing. That question remains as open as ever. In the late 1920s and early 30s, physicists faced a problem. Quantum mechanics worked beautifully for non-relativistic particles, but it couldn't handle situations where particles moved at speeds close to light or where particles could be created and destroyed. Dirac made progress by developing a relativistic equation for the electron, which predicted antimatter, but a complete framework required something more radical. What emerged was quantum field theory, and it changed how we think about what particles are. In classical physics, a field is a quantity that has a value at every point in space and time. The electromagnetic field assigns electric and magnetic field strengths to each location. A temperature field assigns a temperature to each point in a room. Fields are smooth, continuous entities spread throughout space. Particles, by contrast, are localized objects that move through space along trajectories. Quantum field theory unifies these concepts by treating particles as excitations of underlying fields. There's an electron field pervading all of space. An electron isn't a little ball moving through this field. It is a localized excitation, a quantum of the electron field. Similarly, photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. Every particle type corresponds to a quantum field, and what we call particles are the field's excited states. This framework naturally handles particle creation and destruction. In classical mechanics, You can't create or destroy a particle. Mass is conserved. But in relativistic quantum mechanics, energy can convert into mass via Einstein's equation E equals mc squared. High-energy photons can produce electron-positron pairs. Particles and antiparticles can annihilate into pure energy. These processes don't make sense if you think of particles as fundamental objects, but they're natural if particles are excitations of fields. Adding energy to the field creates excitations. Removing energy removes them. The quantum in quantum field theory comes from treating the field itself as a quantum system. In classical field theory, the electromagnetic field at each point has a definite value. In quantum field theory, the field value becomes an operator, a mathematical object that doesn't commute with other operators. This introduces uncertainty. You can't simultaneously know the field value and its rate of change with perfect precision, just like you can't simultaneously know a particle's position and momentum. The field can be in different quantum states. The vacuum state is the lowest energy state, where no particles are present. But even the vacuum isn't empty. The field still exists, and quantum fluctuations cause it to vary slightly around its minimum value. These are vacuum fluctuations, temporary excitations that pop in and out of existence too quickly to be directly observed, but have measurable effects. One such effect is the Casimir force. Place two uncharged metal plates very close together in a vacuum. Quantum. Fluctuations of the electromagnetic field between the plates are restricted to wavelengths that fit between the plates, while outside the plates, all wavelengths are allowed. This creates a difference in vacuum energy density, producing a tiny attractive force between the plates. The effect has been measured and matches the theoretical prediction. Virtual particles are another consequence of quantum fields, though the term is misleading. In calculations, physicists use a technique called perturbation theory, where they expand a quantity as a power series and compute it term by term. Each term can be represented by a Feynman diagram, a pictorial representation showing particles interacting and exchanging other particles. These exchange particles are called virtual because they don't satisfy the normal energy-momentum relation that real particles do. They exist only as internal lines in the diagram, never as external observable particles. Virtual particles are mathematical tools, not physical objects. They represent contributions to a calculation, intermediate steps in evaluating probabilities. When people say virtual particles pop in and out of existence or mediate forces, they're speaking loosely. What's really happening is that quantum fields interact in ways that can be systematically calculated using diagrams, and the internal lines in those diagrams correspond to off-shell propagators in the math. The particles aren't real in the sense of being detectable. They're accounting devices. This matters because virtual particles are often invoked to explain phenomena like the Heisenberg uncertainty principle, allowing energy conservation violations for brief times. That's not quite right. The uncertainty principle doesn't allow violations. It constrains what can be simultaneously known. Virtual particles aren't borrowing energy from nowhere. They're terms in a calculation that happens to converge to the correct physical answer. Quantum field theory also handles force as particle exchange. In classical physics, forces are described by fields. An electron feels a force because it's in an electromagnetic field. In quantum field theory, the electromagnetic interaction between two electrons is described by exchanging photons. One electron emits a photon, the other absorbs it, and the momentum transfer produces what we call a force. These exchanged photons are virtual, internal to the calculation. This picture extends to all fundamental forces. The strong force, which holds quarks together inside protons and neutrons, is mediated by gluons. The weak force, responsible for certain types of radioactive decay, is mediated by W and Z bosons. Gravity, in theories attempting to quantize it, would be mediated by gravitons. Each force corresponds to a field, and interactions involve exchanging quanta of that field. The standard model of particle physics is a quantum field theory describing 3 of the 4 fundamental forces, and all known elementary particles. It's been tested to extraordinary precision, with predictions matching experiments to many decimal places. The discovery of the Higgs boson in 2012 confirmed the last missing piece of the standard model, validating the framework. But quantum field theory has conceptual oddities. One is that fields are defined everywhere in space, even in regions where no particles are present. The field exists, silently, at every point. It's not just a mathematical convenience. The field carries energy and momentum even in its vacuum state. This ubiquitous presence is strange if you're used to thinking of particles as localized objects. Another oddity is renormalization. When you try to calculate certain quantities, like the mass or charge of an electron, you get infinite answers. This happens because quantum fluctuations at arbitrarily high energies contribute to the result, and summing them produces divergences. The solution is renormalization, a procedure where you absorb the infinities into redefined parameters and work with measurable quantities instead of the bare parameters that appeared in the original equations. This sounds like a mathematical trick, and historically, many physicists were uncomfortable with it. But it works. Renormalization produces finite, accurate predictions, and it's now understood as a consequence of effective field theory. The standard model is probably not the final theory, just a low-energy approximation to something deeper. The infinities signal that the theory breaks down at very high energies, but they don't affect predictions at accessible energies once you properly account for the theory's limited range of validity. Quantum field theory also changes what it means for particles to be identical. In quantum mechanics, 2 electrons are indistinguishable. Swap them, and you can't tell the difference. But in quantum field theory, there's a deeper reason. There's only one electron field. Every electron is an excitation of that same field. They're not just similar. They're manifestations of the same underlying entity. This gives a natural explanation for why all electrons have exactly the same mass and charge. They're different excitations of the same field, so they share the field's properties. The framework extends to curved spacetime, though incompletely. Quantum field theory in curved spacetime describes quantum fields on a classical curved background, like the spacetime around a black hole. This leads to phenomena like Hawking radiation, where black holes emit particles due to quantum effects near the event horizon. But a fully quantum theory of gravity, where spacetime itself is quantized, remains elusive. String theory and loop quantum gravity are attempts to go beyond quantum field theory, treating spacetime and matter on an equal footing. These theories replace point particles with extended objects like strings or quantized spacetime geometry itself. But they're speculative, with no experimental confirmation yet. For all accessible energies, quantum field theory remains the best description we have. In practical terms, quantum field theory is the language of particle physics. Experimentalists at colliders like the Large Hadron Collider test its predictions. Theorists use it to calculate scattering amplitudes, decay rates, and cross-sections. It's the foundation of modern physics, as central to contemporary science as Newtonian mechanics was in the 18th century. Yet it's also abstract and unintuitive. Fields are everywhere. Particles are nowhere specific until measured, and the vacuum seethes with fluctuations. It's a far cry from the billiard ball picture of classical particles. But it's empirically successful and conceptually coherent, even if it requires rethinking what matter is at the most basic level. Particles aren't little objects. They're ripples in fields that stretch across the universe, quantized and interacting in ways that produce the complex structure of the world we observe. In 1948, Claude Shannon published a paper that founded information theory, providing a mathematical framework for quantifying information and uncertainty. Decades later, physicists began realizing that this framework could offer new insights into quantum mechanics. Instead of asking what particles are doing or what the wave function represents, you could ask, what information do we have, and how does it change when we make measurements? The basic unit of classical information is the bit, which can be 0 or 1. A coin flip gives you one bit of information. Knowing the outcome reduces your uncertainty from 2 possibilities to 1. Shannon defined entropy as a measure of uncertainty or missing information. For a system that could be in one of several states with different probabilities, the entropy quantifies how uncertain you are about which state it's actually in. Quantum information introduces the qubit, a quantum 2-level system like an electron's spin. A qubit can be in a superposition of 0 and 1, not just one or the other. This isn't the same as classical uncertainty, where the coin has already landed but you haven't looked yet. The qubit genuinely doesn't have a definite value until measured. The superposition is a different kind of state entirely. When you measure a qubit, you get one bit of classical information, either 0 or 1. But the qubit in superposition contained more structure than that single bit. The superposition coefficients encode amplitudes and relative phases, information about how the 0 and 1 states are combined. This information is lost when you measure, collapsed into a single definite outcome. Measurement destroys quantum information while creating classical information. Entanglement adds another layer. 2 qubits can be entangled so that measuring one instantly tells you something about the other, even at a distance. The pair has definite correlations, but neither qubit individually has a definite state. The information is stored non-locally, in the relationship between the qubits rather than in either one separately. This is fundamentally different from classical correlations, which can always be explained by shared information determined in advance. Von Neumann entropy quantifies quantum uncertainty. For a quantum state described by a density matrix, the entropy measures how mixed the state is. A pure state, one with no classical uncertainty, has 0 entropy. A maximally mixed state, where all possibilities are equally likely, has maximum entropy. This entropy increases when a quantum system decoheres, as interaction with the environment converts quantum superpositions into classical mixtures. This connects to the second law of thermodynamics, which says entropy tends to increase. In closed systems, quantum evolution is unitary, meaning entropy stays constant, information is never lost. But real systems aren't closed. They interact with environments, and when you trace over the environmental degrees of freedom you can't observe, the system's entropy increases. Information hasn't disappeared. It's leaked into the environment, becoming inaccessible. This is exactly what happens during decoherence. The information theoretic perspective clarifies the measurement problem without necessarily solving it. Measurement is an interaction that entangles the system with a measuring device, which then entangles with the environment. Information about the system becomes encoded in increasingly large and complex environmental degrees of freedom. From the system's perspective, this looks like loss of coherence and increase of entropy. But from the perspective of the universe as a whole, the evolution is still unitary and information preserving. This framework is particularly useful in quantum computing. A quantum computer manipulates qubits in superposition and entangled states to perform calculations. The computation is a sequence of unitary operations that transform the initial quantum state into a final state encoding the answer. When you measure the final state, you extract classical information, but you've done so after exploiting quantum information processing unavailable to classical computers. Quantum error correction uses information theory to protect quantum states from decoherence. The idea is to encode a single logical qubit into multiple physical qubits in such a way that errors affecting individual physical qubits can be detected and corrected without measuring, and thus destroying, the logical qubit's quantum state. This requires clever use of entanglement and measurement strategies, all grounded in quantum information theory. Entanglement entropy measures how much entanglement exists between two parts of a system. If you divide a quantum system into two regions and trace over one region, the entropy of the remaining region quantifies the entanglement between the regions. This turns out to be important in black hole physics and quantum gravity, where the entropy of a region relates to the area of its boundary, suggesting a deep connection between information, entanglement, and space-time geometry. The holographic principle, emerging from string theory and black hole thermodynamics, proposes that all the information in a volume of space can be encoded on the boundary of that volume. This is analogous to a hologram, where a two-dimensional surface encodes a three-dimensional image. The principle suggests that quantum gravity might be fundamentally about information on boundaries rather than events in volumes, a radical reconceptualization of space-time. Black hole information paradox brings these ideas into sharp focus. When matter falls into a black hole, information about its quantum state seems to be lost when the black hole eventually evaporates via Hawking radiation. But quantum mechanics says information can't be destroyed. The paradox has driven decades of research into quantum gravity, with proposed resolutions involving subtle correlations in the Hawking radiation, or modifications to the space-time structure near the horizon. Quantum teleportation, discovered in the early 1990s, is another information-theoretic phenomenon. You can transfer a quantum state from one location to another using entanglement and classical communication, without the quantum state ever traveling through the space between. The protocol requires 2 bits of classical information and 1 unit of shared entanglement to teleport 1 qubit. No quantum information travels faster than light, but the state is destroyed at the sender and recreated at the receiver. This isn't teleportation in the science fiction sense. You can't send matter or energy faster than light. You need a classical communication channel to complete the protocol, and that's limited by light speed. But it demonstrates that quantum information behaves differently from classical information. The state can be transferred without anyone learning what the state is, preserving quantum correlations that would be destroyed by measurement. The no-cloning theorem is another information-theoretic result. You can't make a perfect copy of an unknown quantum state. Classical information can be copied trivially, but quantum information can't. This follows from the linearity of quantum mechanics. If cloning were possible, it would allow you to violate the uncertainty principle by making many copies of a state and measuring different properties on different copies. The impossibility of cloning protects quantum mechanics from internal contradiction. These information-theoretic features have practical applications in quantum cryptography. Quantum key distribution uses the no-cloning theorem and the disturbance caused by measurement to create provably secure communication channels. Any eavesdropper trying to intercept the quantum states would disturb them in detectable ways, alerting the legitimate users. Security is guaranteed by the laws of physics, not just computational difficulty. Thinking about quantum mechanics in terms of information doesn't commit you to a particular interpretation. Copenhagen, many worlds, and pilot wave theory can all be reformulated in information-theoretic language. The difference is what the information is information about. Is it information about measurement outcomes, about which branch you're in, about hidden particle positions, or about objective physical states? The math works the same way regardless. But the information perspective does suggest that quantum mechanics might be fundamentally about constraints on information processing rather than about particles and waves. The theory tells you what correlations are possible, what information can be extracted, how information flows during interactions. Reality, from this view, is something like the structure of possible information states and their transformations. This connects to digital physics and it from bit ideas, proposals that reality is fundamentally informational. These are speculative, far from mainstream, but they illustrate how seriously some physicists take the role of information in fundamental physics. Whether information is a useful language for describing physical processes, or whether physical processes are actually made of information, remains an open question. What's clear is that information theory provides powerful tools for understanding quantum mechanics. It clarifies entanglement, explains decoherence in thermodynamic terms, enables quantum technologies, and connects quantum mechanics to other areas like black hole physics and quantum gravity. The wave function might be mysterious, but information flow is calculable and concrete, offering a handle on quantum phenomena that doesn't. Requires settling deep interpretive questions about what's really real. Quantum mechanics gets misused, not occasionally or accidentally, but systematically and often deliberately, to support claims that range from merely confused to outright fraudulent. The misuse follows predictable patterns, exploiting genuine strangeness in the theory while ignoring the actual constraints physics imposes. Understanding what quantum mechanics doesn't say is as important as understanding what it does. Start with consciousness and the observer effect. The claim goes like this. Quantum mechanics says observation collapses the wave function. Observation requires consciousness. Therefore, consciousness affects physical reality at the quantum level. This opens the door to ideas like mind over matter, consciousness creating reality, or quantum healing, where focused intention manipulates quantum states in your body to cure disease. The problem is that observation in quantum mechanics doesn't mean what it means in everyday language. A measurement is a physical interaction that entangles the quantum system with a macroscopic apparatus. The apparatus doesn't need to be conscious. A photographic plate registers particle impacts without anyone looking at it. A Geiger counter clicks without anyone listening. A rock lying on the ground is constantly being measured by its environment. None of this requires minds. The confusion traces partly to unfortunate terminology, and partly to speculative ideas from physicists like Wigner, who suggested consciousness might play a role in collapse. But these ideas were never mainstream and aren't supported by evidence. Decoherence explains why measurements produce definite outcomes without invoking consciousness. The quantum to classical transition happens through environmental interaction, not through minds observing things. This matters because the consciousness interpretation has been used to market everything from alternative medicine to self-help programs claiming you can manifest reality through quantum intention. These products invoke quantum mechanics as a veneer of scientific legitimacy, while ignoring that the theory makes precise mathematical predictions that don't include conscious observation affecting distant or macroscopic systems. Free will is another area where quantum mechanics gets conscripted. The argument is that quantum randomness introduces indeterminism into physics, and indeterminism creates room for free will that wouldn't exist in a deterministic universe. Therefore, quantum mechanics proves, or at least allows, for free will. This doesn't work on multiple levels. First, randomness isn't freedom. If your decisions are determined by random quantum events in your neurons, You're not exercising free will any more than if they were determined by classical physics. Random isn't the same as chosen. Second, the quantum randomness that exists in the Copenhagen interpretation, or that emerges from self-location uncertainty in many worlds, doesn't obviously connect to human decision-making. The brain is warm and wet, conditions where decoherence happens extremely fast. Quantum coherence doesn't persist long enough to affect neural processing in any meaningful way. There are speculative theories about quantum effects in biology, like quantum coherence in photosynthesis or bird navigation. These are legitimate research areas. But they're about quantum mechanics helping biological systems perform specific functions more efficiently, not about quantum mechanics enabling consciousness or free will. And even in these cases, the effects are carefully isolated by evolution, protected from decoherence, not relying on consciousness or intention. The claim that quantum mechanics undermines materialism or supports mysticism is also common. The reasoning is that quantum mechanics shows reality is observer-dependent. Particles don't have definite properties until measured, and the wave function is just information or probability. Therefore, the physical world isn't objectively real. Consciousness is fundamental, and ancient mystical traditions that emphasize the role of mind in reality were right all along. But quantum mechanics doesn't say the physical world isn't real. Different interpretations disagree about what's real, whether it's the wave function, particle positions, or multiple branches, but they all agree there's something physical happening that follows mathematical laws. The theory is about matter and energy, fields and interactions, not about consciousness or spirit. Saying the wave function represents information doesn't mean reality is made of information, any more than saying a weather forecast represents information means weather is made of information. The conflation happens because quantum mechanics doesn't give a classical picture of definite properties existing independently of measurement. But refusing to provide a classical picture isn't the same as saying nothing exists. It's saying that reality at the quantum level doesn't map onto classical intuitions. That's not mysticism. It's physics telling you that your intuitions, honed by experience with large, slow objects, break down at small, fast scales. Another misuse involves quantum entanglement and non-locality. Entanglement shows correlations between distant particles, which gets interpreted as proving everything is connected, that separateness is an illusion, that actions here affect things there instantaneously. This gets used to justify ideas about telepathy, distant healing, or cosmic consciousness. Entanglement does show non-local correlations, but it doesn't allow signaling or causal influence. You can't use entanglement to send messages faster than light or to affect distant systems. The correlations are statistical, only visible when you compare measurement results from both locations. From either location alone, the results look random. The non-locality is in the correlations, not in controllable influences. Moreover, entanglement is fragile. It's destroyed by decoherence, typically very quickly for any macroscopic system. Two people's brains aren't entangled just because they met once. Their quantum states decohered immediately through environmental interaction. Entanglement requires careful isolation, the kind achieved in physics labs with extreme effort, not something that happens spontaneously between distant objects. Quantum mechanics also gets invoked to explain paranormal phenomena. The claim is that since quantum mechanics is weird and poorly understood, and paranormal phenomena are weird and poorly understood, maybe quantum mechanics explains the paranormal. This is argument by analogy, without mechanism. Quantum mechanics is precisely formulated and extensively tested. It doesn't predict telepathy, precognition, or psychokinesis. If these phenomena existed, they'd require new physics, not just quantum mechanics applied creatively. The attraction is understandable. Quantum mechanics is genuinely strange. Wave-particle duality, superposition, entanglement, all violate classical intuitions. If reality can be that weird at the quantum level, maybe it's weird in other ways too. But weirdness isn't fungible. The specific weirdness of quantum mechanics is constrained by mathematical structure and experimental tests. You can't borrow quantum weirdness to justify arbitrary weirdness elsewhere. Actual physicists are generally careful about these distinctions. When they talk about observers, they mean measuring devices. When they discuss interpretation, they acknowledge uncertainty and avoid claiming their preferred interpretation is proven. When they encounter questions about consciousness or free will, they usually note these are outside physics domain, or they discuss them carefully without claiming quantum mechanics settles the issues. The misuse comes from popularizers, entrepreneurs, and sometimes from physicists speaking outside their expertise. Books and documentaries present quantum mechanics as proving consciousness creates reality or that thoughts affect matter. Products get marketed using quantum language without quantum content. The word quantum becomes a synonym for mysterious and powerful, detached from its actual meaning in physics. This matters because it undermines public understanding of science. People come away thinking quantum mechanics is mystical or that physics has proven the power of positive thinking. When they encounter actual physics, it can feel like a bait and switch. The real theory is mathematical and precise, not vague and consciousness-centered. The disappointment can breed cynicism about science generally. It also matters because it allows exploitation. People spend money on quantum healing devices that don't use quantum mechanics. They make medical decisions based on quantum consciousness claims that aren't supported by evidence. They reject conventional medicine in favor of alternatives that invoke quantum language as authority. The appropriate response isn't to pretend quantum mechanics is simple or intuitive. It's strange, and that strangeness is worth conveying. But the strangeness is specific, mathematical, and constrained by evidence. Quantum mechanics doesn't say consciousness creates reality. It doesn't enable telepathy. It doesn't prove mysticism. It describes how matter and energy behave at small scales, and that behavior is different from everyday experience, but not magical. Understanding what quantum mechanics doesn't say requires understanding what it does say. The wave function evolves according to the Schrödinger equation. Measurements produce definite outcomes with calculable probabilities. Entangled systems show correlations stronger than classical physics allows. These are precise claims, tested and confirmed. Everything else, the speculation about consciousness or reality or mysticism, is interpretation or extrapolation, often going far beyond what the theory supports. Quantum mechanics is remarkable enough without embellishment. It revolutionized physics, enabled technologies from lasers to semiconductors to MRI machines, and revealed a natural world far stranger than anyone expected. That's the real story. The rest is noise. Quantum mechanics works. The predictions match experiments to extraordinary precision. Technologies built on quantum principles function exactly as the theory says they should. But nearly a century after the theory's formulation, physicists still argue about what it means. What questions remain genuinely open? And what does the current state of research tell us about where the field is headed? The measurement problem remains central. Despite decoherence explaining why superpositions appear to collapse, the question of what actually happens during measurement isn't settled. Many worlds says all outcomes occur in different branches. Copenhagen-style interpretations say the question is meaningless, or that the wave function isn't a complete description of reality. Pilot wave theory says particles always had definite positions. These interpretations make the same empirical predictions for any experiment we can currently perform, which is why the debate persists. Some physicists argue this makes interpretation a non-issue. If all interpretations give the same predictions, the choice between them is metaphysical preference, not physics. Others counter that understanding what the theory describes matters for extending it to new domains like quantum gravity, where interpretational choices might make different predictions. A few researchers think new experiments might eventually distinguish interpretations, though so far no decisive tests exist. Bell's theorem and experimental violations of Bell inequalities have constrained the options significantly. Any interpretation reproducing quantum predictions must be non-local in some sense, or it must reject realism about measurement-independent properties, or both. This rules out local hidden variable theories where particles have definite properties determined in advance. The universe is either non-local, or properties don't exist until measured, or reality is more complicated than classical intuitions allow. Recent experiments have closed loopholes in Bell tests. Earlier experiments left room for skeptics to argue that local realism might still be viable if you accounted for detector inefficiencies or allowed communication between measurement sites. Modern experiments close these loopholes, using efficient detectors and space-like separated measurements where no signal could travel between them. The violations of Bell inequalities are robust. Nature really does exhibit these non-local correlations. This doesn't prove any specific interpretation correct, but it clarifies what any viable interpretation must accommodate. The correlations are real and can't be explained by pre-existing local properties. How you interpret that fact, whether as non-local guidance laws, branching universes, or limits on what properties can meaningfully be attributed to unmeasured systems, is where interpretations differ. Another open area is the quantum to classical transition. Decoherence explains why quantum systems appear classical when they interact with environments, but it doesn't explain why we experience definite outcomes. In many worlds, all outcomes occur and we experience one branch. But why this branch? The Born rule, which gives probabilities for measurement outcomes, works perfectly for making predictions, but lacks a deeper derivation in some interpretations. Many worlds proponents have tried deriving it from decision theory or symmetry arguments, but these derivations remain controversial. Related to this is the problem of time in quantum mechanics. The Schrödinger equation treats time as a parameter, not an observable like position or momentum. This works fine in non-relativistic quantum mechanics, but creates problems when you try to quantize gravity. In general relativity, time isn't absolute, and in quantum gravity approaches like Wheeler-DeWitt equation, time might emerge from something more fundamental. Understanding how time works in quantum theory connects to deep questions about the universe's quantum state and whether it evolves at all in some global sense. Quantum field theory remains the working framework for particle physics, but it's not complete. It doesn't include gravity. The Standard Model describes 3 forces, but leaves gravity classical. Attempts to quantize gravity face technical and conceptual obstacles. String theory and loop quantum gravity are leading approaches, but neither is confirmed experimentally, and both remain works in progress. Understanding how quantum mechanics and gravity fit together is perhaps the biggest open problem in fundamental physics. Black holes present a testing ground for quantum gravity. Hawking radiation suggests black holes have entropy proportional to their surface area, not their volume, hinting at holographic principles where information in a volume is encoded on its boundary. The black hole information paradox, whether information is lost when black holes evaporate, has driven research into quantum properties of spacetime. Recent work suggests information is preserved through subtle correlations in the radiation, but a complete understanding requires quantum gravity. Quantum Foundations research continues, investigating the structure of the theory itself. Why does quantum mechanics have the mathematical form it does? Could there be theories with different structures making different predictions? Generalized probabilistic theories explore this, finding that quantum mechanics sits between classical probability theory and more exotic possibilities. Some features, like the impossibility of signaling faster than light, seem to constrain the structure significantly. Contextuality is another active research area. This is the idea that measurement outcomes depend not just on what you measure, but on what else you could have measured, the context of the measurement. Classical theories aren't contextual. Quantum mechanics is. Understanding contextuality helps clarify what makes quantum mechanics distinctly quantum and connects to practical questions in quantum computing, where contextuality is a resource for quantum advantage. Quantum information theory has become a major field, not just for applications like quantum computing and cryptography, but for foundational insights. Entanglement is now understood as a resource that can be quantified and manipulated. Information theoretic approaches to quantum mechanics bypass some interpretational questions by focusing on what information can be extracted and how it flows, though this doesn't eliminate interpretation, just reframes it. Macroscopic quantum effects remain a frontier. Superconductivity and superfluidity are quantum phenomena at large scales, but they're well understood. More speculative is whether quantum coherence plays functional roles in biology beyond isolated cases like photosynthesis. Some researchers investigate quantum effects in neural processes, though skepticism is widespread given rapid decoherence in warm, wet environments. If large-scale quantum effects do occur biologically, it would be remarkable, but evidence is currently weak. Quantum computing is advancing rapidly, not just technologically, but conceptually. Understanding what problems quantum computers can solve efficiently and why illuminates the structure of quantum mechanics itself. Quantum error correction, quantum algorithms, and the border between classical and quantum computation all provide insights into the theory's foundations while driving practical developments. Which interpretations do working physicists favor? Surveys show no consensus. Copenhagen or related instrumental approaches remain common, especially among physicists focused on applications rather than foundations. Many worlds has grown in popularity, particularly among younger physicists and those in quantum information. Pilot wave theory has a small but dedicated following. Some physicists adopt a pragmatic agnosticism, using whichever interpretation is convenient for the problem at hand. The lack of consensus isn't necessarily a problem. As long as interpretations make the same predictions, choosing between them doesn't affect research. But it does affect how physicists think about extensions to the theory. If you take many worlds seriously, you might think about quantum cosmology differently than if you take Copenhagen seriously. Interpretational preferences can guide research directions, even if they don't change predictions in well-tested regimes. Experimental tests that might distinguish interpretations are rare and difficult. Some researchers have proposed experiments involving macroscopic superpositions, or tests of collapse models, modifications to quantum mechanics that introduce objective collapse mechanisms. Collapse models predict deviations from standard quantum mechanics that might be detectable with sufficiently sensitive experiments. So far, no deviations have been found, but the search continues. The future of quantum foundations likely involves tighter connections between interpretation, quantum gravity, and quantum information. As we probe more extreme regimes, cosmology, black holes, the Planck scale, interpretational choices might start making different predictions. Or, the development of quantum gravity might force a particular interpretation by revealing what the wave function describes in a fully quantum space-time. Alternatively, the interpretational debates might never be resolved empirically. They might remain metaphysical choices that reflect different priorities about what scientific theories should explain. Some physicists are comfortable with this. Others find it unsatisfying, believing that science should tell us not just what will happen, but what's actually there. What's clear is that quantum mechanics isn't finished. As a practical tool, it's complete and precise. As a description of reality, it's still puzzling. The theory has been tested more thoroughly than any other in physics and has never failed. But what it's telling us about the nature of reality, whether it's many worlds or one world guided by hidden variables, or a world that only becomes definite when measured, remains contested. Living with this uncertainty is part of modern physics. The theory works perfectly while its interpretation remains unclear. We use quantum mechanics to build devices, make predictions, and explore the universe, all while arguing about what the theory means. That's uncomfortable for those who want definite answers, but it's honest. The math is clear. The implications for the nature of reality are not. And maybe that's the most important thing quantum mechanics teaches us, that understanding how things behave doesn't always tell you what they are.